Welcome back, AP Physics, to some notes on energy. Today we're going to be learning about the different kinds of energy that a system can contain. But first, let's review what work is, just because that's going to be helpful for us moving forward. So remember that work is equal to the dot product of force and some displacement. Okay. If this force is varying, what we can do is we can do the force that has some x portion, and we'll do the integral with respect to that x.
So the first kind of energy that we're going to be trying to figure out is what we call kinetic energy. Now, kinetic energy is the energy of motion, right? If I push on an object over some distance, right, I'm going to be causing it to move. So there's going to be some energy that is related to motion, and that's what we call kinetic. So the book gives us this gunky looking derivation where it says there's some chain rule manipulations. We're going to avoid that. There's actually a much simpler and algebraic derivation for kinetic energy that we can find. So let's look back up here at our definition for work. So it is force times some displacement. Okay. Now, if we want to relate that to motion, right, we know Newton's second law, so we can write work is equal to mass times acceleration times this displacement. That squeak in the background is Bosco. But we're not done. This is not where we would like to leave things. We would like to relate it to some initial and final velocities. Let's consider, all right, that box, or let's make it a some sort of box on wheels, right? It's a really chunky skateboard. Okay. Now I have some initial velocity that this box has, and I'm going to apply my force over that distance, right? So that now it has some final velocity, right? And here's our delta x. Right? So I would like to relate these things together. So if we think back to kinematics, there was that one equation that I kind of neglected to show you, but it is the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration and then your displacement or the distance traveled. Okay. So what we can do is we can substitute in our velocities for the acceleration and the displacement. So what we're going to do is we are going to solve for this. And actually, let's go back there. We're going to solve for this and then substitute that in over here. Okay. So let's solve for that. So a delta x is equal to squared minus the initial velocity squared divided by 2. So let's plug that in. Work is equal to mass. And right, this 2 is just a constant, so it's going to be half mass velocity final squared minus velocity initial squared. Okay, and then let's write it out in a slightly different format. So it's 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. Now, both of these forms are both accurate. You can use either or. But we still don't have an answer for what kinetic energy is, right? We have the amount of work for an object that is changing its velocity, but we don't know what kinetic energy is. But if we remember that work is the change in energy, then we can tell here that this is simply the change in kinetic energy, since it's a difference between a final and initial motion. So we can write this work down as the change in kinetic energy. Now, the textbook is just going to use a K, so I will be using that for the future. The next kind of energy we want to consider is potential energy. And so this is going to be an energy depending on the difference in positions or the separation of two gravitational objects. So there's multiple kinds of potential energy. For the most part, we are only going to be considering gravitational. Now, next semester, we will be considering electric potential energy and what's also called electric potential. Don't need to know about that right now, but that potential energy is going to be the difference in position or the separation of two electrically charged objects. So in this case, we're dealing with gravitational objects. So the first thing that we want to think about is in which direction is our force? And for us, we are going to be right on Earth. And so our force is always going to be straight downwards, right? So again, we want to remember that work is the dot product of force and some displacement. Now, the dot product means that we are looking at the same components in the same direction. And since force is always going to be in the vertical direction for us, that means that the displacement that is related to gravitational potential energy is always going to have to deal with that vertical direction as well. So if I go for a jog and I don't change my altitude whatsoever, then my gravitational potential energy has stayed exactly the same. No work has been done on me. But if any of you have gone for a run or you've gone for a bike ride, you know that when you're going down a hill, gravity is doing work to give you that kinetic energy, right? The potential energy that you have that was stored in your separation from the center of the earth is being turned into kinetic energy. So let's write this out. We know that it is going to be the force of gravity multiplied by that displacement. Now, remember, I said the displacement is always going to be in that vertical direction. So the book wants to define it as mg and then delta y, or mg y final minus mgy initial. That's gross. That's dumb. Because it's just the height, guys, right? If I want to know the work that is done, it's going to be some mgh final minus mgh initial. Okay? This is how I learned it. This is how Dad does it. And it's worked out well so far. So we are going to be writing it like this in my AP Physics class, but this is the gravitational potential energy. So if we consider the example on page 164, right there is a ramp that some guy is using to pull a fridge up on a dolly. All right, so here's our dolly, here's our refrigerator. Okay, oh man, it's such a beautiful picture. No one would. There's the handle, right? Another handle, okay? And our guy is pushing this thing up the ramp. Excellent. Sweet. So what the problem wants to consider is, does the ramp change the amount of work our guy has to do? And the answer is no, right? This height is still the same, right? The change in height from the ground floor to the top floor is still the same. But the force that he has to exert to push it up is going to change, right? So this is another problem where we could change the axes. Right, but this distance here, right? This distance, this delta r is longer. And so what you've done is you've made the process easier because you've given your person a longer distance to travel, which means that the force is going to go down. And so when we think about the amount of work, we can vary the amount of force, right? So work is always going to be the same, but I can make my force less by making my distance, my delta r, much bigger, right? So that's what the ramp does. It makes the job easier to do because the force is less, but the work is still the same, right? It is probably easier to write that single page paper over several nights than it is to write it in one single evening. And just so we're clear, we are going to represent potential energy with a capital U. And for gravitational potential energy, that's going to be mgh. The last kind of energy we're going to talk about today is called internal energy. But you probably know it more as thermal. Now, we call it internal energy because it's this motion of molecules on the atomic level, right? Or the molecular level, I guess. And so this is energy that is now stored not in the object entirely, but each of the individual molecules of our object. So let's consider for a moment a situation that is a little bit more realistic. So let's draw a surface here, and we'll put our physics box. We should give our box a name sometime. We'll put our physics box here, and we're going to move it over to here. So we're going to have some delta x and apply a force to it. Right? So if this surface was frictionless, then at some point we would have a non-zero velocity right after we began pushing it, right? We would be giving it kinetic energy. And this is going to be the case, right? If I push on this box across the surface, well, it is going to move. I'm going to have to give it some kinetic energy for it to move. But we know all too often that if I push something across the table, right, it is going to eventually stop. And we know this is because of friction, right? We talked about this in the previous unit. So this friction is going to be giving us our thermal energy. So this is where the energy is going to go. Friction is going to slow down our box, and it's going to turn this energy into the thermal energy that we're familiar with. Now, there isn't a direct equation that I can give you for the internal or thermal energy, but it's still going to be related to the work. So let's say I do work on this object, and right, it's this force times displacement. Now, in the end, if the change in energy causes us to have a kinetic energy that's zero, and right, the height hasn't changed, then we know that this is just a total change in the internal energy. The last thing we need to talk about is conservative and non-conservative forces. So in the book, it gives you two different conditions that need to be fulfilled for that to be the case. For us, for the most part, it's just going to be easy enough if we know that the mechanical energy is not conserved. And we defined the mechanical energy mechanical, to be the addition of the kinetic energy and the potential energy. So if this total value here isn't the same after something occurs, then we know that the forces involved were not conservative. Right? So friction is going to be one of these, right? If friction is in there, usually we lose some kinetic energy like we did before. So with our box, right, being moved some distance, right? And let's say it has some kinetic energy, right? But in the end, the kinetic energy is zero, right? Let's say this was just 5 joules of energy, and in the end we have 0 joules. But notice that our displacement is completely horizontal. Since this is the case, the potential energy initial is equal to the potential energy final. So our addition of the mechanical energy at the very beginning was the initial plus the initial is not equal to kinetic energy final plus the potential energy final, right? So this makes the frictional forces non-conservative, right? Now, if we consider something that's frictionless, let's say we have some skateboarder on a ramp, right? Over here, let's say that they have a kinetic energy that is 0 joules and a potential energy that is 20. Now, at the bottom here, right, our skateboarder has fallen a distance, and that means that the kinetic energy has to increase. Let's give him half, right? And the potential energy is 20. And at some time later, when they're at the same elevation, right, they are going to be slowed down by the gravitational force. And they will have, whoops, I did not write that. That needs to be 10. They will have been slowed down by the gravitational force and will have gained potential energy. And they will be stopped once more, so their kinetic energy will go back to 0. These are conservative forces. The gravitational force is conservative.